The mysteries of the universe have fascinated us for millennia, but recently, due to the advancement of science, we have become able to uncover some of the biggest secrets of the universe. However, there are still mysteries that have yet to be resolved. The biggest challenge right now for scientists is to establish one theory that can explain everything. This theory will be named the theory of everything. But is it possible for scientists to establish such a theory? Can string theory be called the theory of everything? Let's find out.
Some people say, if we find the theory of everything, the crowning achievement of modern science, ever since humans first began to ask, what is the world made of? Are we going to have wonders, technological wonders? Am I going to get better color television? Am I going to get better cable reception? Am I going to get a better internet? Well, the short-term answer is no. It's not going to affect your life or the life of anyone directly. But look at it this way. This theory of everything is also a theory of space and time and the universe itself. It will answer some of the deepest philosophical, theological questions of all time. What happened before Genesis, chapter 1, verse 1? What happens if time can be bent into a pretzel? What happens if space has holes in it? What happens if you could somehow manipulate space and time itself? These questions are far beyond the theories of Einstein. Einstein's theory breaks down at the instant of the Big Bang, where it's useless. Einstein's theory breaks down at the center of a black hole. What lies on the other side of a black hole? What lies on the other side of a Big Bang? Einstein's theory are useless because they simply blow up at that point. This is where a theory of everything comes in. String theory, being a theory of everything, actually allows us to go before the Big Bang, where there might have been a multiverse of universes. With our universe being a bubble, we live on the skin of the bubble is expanding, and there are other bubbles out there floating in 11-dimensional hyperspace. And these bubbles, in turn, are connected perhaps by gateways, by tubes. These are called wormholes, and we physicists take them very seriously. These wormholes may or may not be stable, we're not sure, but they are definitely part of the equations of the theory of everything.
In the world of theoretical physics, the theory of everything is a fascinating concept. It's an ambitious idea to create a single framework that can explain all the fundamental forces and particles in the universe. To understand it better, let's take a look at its history and why it matters in physics. The concept of a theory of everything has its roots in the early days of modern physics. One significant milestone was Sir Isaac Newton's work in the late 17th century when he introduced the laws of motion and gravity. While this was a big step forward, it couldn't cover everything. It couldn't explain the behavior of particles on a tiny scale or at very high speeds. In the 19th century, James Clerk Maxwell made a significant contribution by uniting electric and magnetic phenomena with his equations, giving us a comprehensive theory of electromagnetism. The early 20th century saw a revolution with Albert Einstein's theories of relativity. Special relativity gave us new insights into space and time, and general relativity extended this to include gravity's impact on space and time. However, these theories raise the challenge of combining them with quantum mechanics. Physics progressed, and it became clear that there was a need for unification. General relativity and quantum mechanics, while individually successful, seemed incompatible when you tried to put them together. General relativity explained the universe on a large scale governed by gravity, while quantum mechanics dealt with the behavior of tiny particles on an atomic and subatomic scale. The theory of everything is significant because it has the potential to offer a comprehensive framework for understanding the universe. It would unify the four fundamental forces and explain the nature of all known particles and their interactions. It's the ultimate guide to the cosmos, revealing the fundamental laws that govern all matter and energy. The search for a TOE has engaged some of the brightest minds in physics, from Einstein to contemporary theorists. It's driven by the desire to understand the fundamental principles underlying the universe. A successful TOE would represent a significant leap in our understanding of the cosmos, much like how general relativity transformed our view of gravity and space. Throughout his life, Einstein sought a unified theory that would reconcile general relativity and quantum mechanics. He believed in the simplicity of nature's laws and thought a single equation could express them. While Einstein made significant contributions, the challenges of unifying gravity and quantum mechanics remained a challenge during his lifetime. Nevertheless, his forward thinking paved the way for future physicists to continue the quest. In the search for a theory of everything, physicists are driven by a deep curiosity to unlock the universe's most profound mysteries. Their goal is to understand the fundamental forces and particles governing the cosmos. This journey involves an effort to unite the two main pillars of modern physics, general relativity and quantum mechanics. Now let's explore why unification is necessary, the challenges it presents, and the different approaches taken to reach this ambitious goal. The need for unification. The fundamental forces of nature have each been independently understood and mathematically explained. However, the real challenge arises from their apparent inconsistency when examined at extreme scales. At macroscopic levels, where gravity is the dominant force, Einstein's general relativity elegantly explains how massive objects warp space-time, creating the force we call gravity. On the other hand, quantum mechanics provides an excellent framework for understanding the behaviors of tiny particles like electrons, quarks, and neutrinos. The trouble begins when these theories are applied together. Trying to merge general relativity and quantum mechanics leads to mathematical contradictions and bizarre predictions, especially near singularities such as those within black holes. These singularities are areas where gravitational forces become infinitely strong and the laws of physics, as we understand them, break down. This breakdown suggests that our current theories are incomplete and need a more comprehensive framework to reconcile these disparities. The primary need for unification is to provide a consistent and coherent description of the universe that applies to all scales, from the cosmic to the quantum. This is what the theory of everything aims to achieve. However, the journey toward unification is packed with challenges. The challenges of unification. The challenges of unifying fundamental forces involve both theoretical and practical complexities. On the theoretical side, one of the main obstacles is combining gravity with quantum mechanics. While quantum mechanics has successfully explained particle behavior, reconciling it with the force of gravity on very small scales remains a significant theoretical challenge. This requires the pursuit of a theory of quantum gravity to harmonize these aspects of physics. Additionally, the effort to unite the electromagnetic force with the weak nuclear force, known as electroweak theory, has made progress at high energies. However, the strong nuclear force, responsible for keeping quarks within particles like protons and neutrons, presents a significant challenge due to its unique nature and the complications it introduces into the unification process. On the practical side, achieving the energy levels needed to explore unified forces is a substantial obstacle. Many unification theories predict phenomena that can only be observed at energy levels currently beyond the capabilities of existing particle accelerators, making experimental validation a challenging goal. Furthermore, cosmic observations offer valuable insights into unification, but they are often indirect and subject to interpretation, introducing uncertainties in the pursuit of a theory of everything. The existence of dark matter and dark energy, which make up a substantial portion of the universe, adds complexity. While these mysterious substances have been incorporated into cosmological models, their true nature and their connection to unification theories remain unsolved questions in the ongoing quest to understand the fundamental forces of the universe. Approaches to unification. Physicists have explored various ways to unify their theories, and three main contenders have emerged. First, there are grand unified theories that aim to bring together the electroweak force, which includes the electromagnetic and weak nuclear forces with the strong nuclear force. These theories suggest that at extremely high energies, these forces used to be the same, which could provide a unified understanding of fundamental forces. GUTS have made progress in explaining certain aspects of particle interactions, but they still need to be confirmed through experiments. Another idea is supersymmetry, which suggests a fundamental symmetry between particles with integer spin, fermions, and those with half-integer spin, bosons. This symmetry could help address important issues in particle physics and potentially lead to unification. However, as of my last update in September 2021, there was no experimental evidence to confirm the existence of supersymmetry, so it remains in the realm of theoretical anticipation. The third approach is string theory, which has gained attention as a leading candidate for a theory of everything. It departs from the idea that fundamental particles are tiny points and introduces the concept of tiny strings that vibrate at different frequencies. These vibrations correspond to various particles and forces in the universe. String theory aims to combine both general relativity and quantum mechanics, potentially reconciling their differences. However, it's still highly theoretical, and its predictions have not yet been confirmed through experiments. This means that the quest for unification is still a work in progress, where theory and experimentation meet and sometimes diverge, shaping our ongoing efforts to understand the fundamental structure of the universe. String theory and the theory of everything. In the quest for a theory of everything, string theory has drawn the attention of physicists. It's a highly theoretical and ambitious approach, suggesting that the basic building blocks of the universe aren't tiny points, but instead tiny vibrating strings. In string theory, particles aren't seen as point-like entities, but as one-dimensional strings that vibrate at different frequencies and create the appearance of various particles with different properties. The aim of string theory is to resolve the challenge of combining general relativity and quantum mechanics by offering a new way to describe the fundamental elements of the universe. String theory began in the early 1970s as an attempt to explain the strong nuclear force. It later expanded to cover not only the strong force, but also the other fundamental forces. This broadening of its scope was seen as a promising step toward achieving a theory of everything by providing a means to unite all forces under one theoretical framework. To understand the core principles of string theory, it's important to know that, according to this theory, the fundamental constituents of the universe are tiny vibrating strings. The different ways these strings vibrate correspond to different particles. For instance, the lowest vibration of a string corresponds to a particle with the properties of a graviton, which conveys gravitational force. String theory also introduces extra dimensions beyond the familiar three spatial dimensions and one time dimension. These extra dimensions are incredibly small and curved in a way that's hard to visualize. These extra dimensions are a critical aspect of string theory because they make the mathematics work and unify the forces. Another key element is supersymmetry, suggesting a deep connection between particles with different spins. This symmetry could potentially address some problems in particle physics and cosmology, providing a more elegant and unified description of the universe. The mathematics of string theory can be quite intricate and often involves advanced mathematical tools, including complex algebra and differential geometry. The theory is expressed through a set of equations that describe how strings move, interact, and vibrate. String theory has received a lot of attention as a potential theory of everything due to its comprehensive nature, its ability to encompass all fundamental forces, and its mathematical elegance. However, it's important to note that its status as a TOE is not yet confirmed. One of the primary appeals of string theory is its potential to unify the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. This unification is made possible through the vibrations of strings, which can give rise to the different force-carrying particles. String theory naturally includes gravity within its framework, potentially resolving the challenge of quantum gravity. In contrast to traditional quantum field theories where gravitons are point-like particles, in string theory, they are described as vibrations of strings. This integration of gravity and quantum mechanics is a significant step toward achieving a theory of everything. Supersymmetry, which is a central component of string theory, has the potential to explain the existence of dark matter, a mysterious substance that makes up a significant portion of the universe's mass. If supersymmetry is confirmed through experiments, it could address a long-standing puzzle in cosmology. The introduction of extra dimensions in string theory offers a novel perspective on the universe. Although these dimensions are compactified and not directly observable, they could hold the key to understanding certain phenomena, such as the hierarchy problem. While string theory offers an appealing vision of a unified framework for understanding the universe, it's not without its set of challenges and controversies. There is no direct evidence to support string theory. String theory often predicts phenomena that occur at energy scales far beyond what current particle accelerators can reach, making it challenging to perform experiments to validate its predictions. String theory has many variants and solutions, which can make it appear overly flexible and difficult to test. The complexity of string theory's mathematics can be a challenge for physicists to work with and verify. The existence of extra dimensions, while mathematically consistent, poses a problem for our intuitive understanding of the universe, as they are compactified to tiny sizes and effectively unobservable. String theory is not the only contender in the quest for a theory of everything. Other approaches, such as loop quantum gravity and certain extensions of the Standard Model, offer alternative visions of unification and the nature of reality. The challenges and obstacles in the quest for a theory of everything. The pursuit of a theory of everything aiming to unify all fundamental forces and particles in the universe is an intriguing intellectual challenge filled with complex problems and ongoing discussions. In this exploration, we'll delve into the significant hurdles faced by physicists in their search for a theory, the limitations of current methods, and alternative viewpoints that question the feasibility of a single, all-encompassing theory. One central challenge is whether it's genuinely possible to unite all fundamental forces and particles. The Standard Model of particle physics has made considerable progress in unifying three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. However, gravity remains a challenging outlier, resisting easy integration. The first challenge involves reconciling quantum mechanics, which explains particle behavior on tiny scales, with general relativity, which describes gravity on cosmic scales. Merging these two theories has proven problematic due to their inherent incompatibility. Quantum mechanics deals with particles, while general relativity describes continuous, smooth spacetime. The pursuit of a theory of quantum gravity, like string theory, remains a substantial challenge, with experimental validation beyond current technological capabilities. The second challenge is the difficulty of conducting experiments to test and validate unification theories. The energy requirements for exploring the unified realm of fundamental forces often exceed the capabilities of existing particle accelerators. For example, grand unified theories propose that at extremely high energies, the fundamental forces were once indistinguishable. However, achieving the energy levels needed for such testing remains an unattainable goal. Similarly, supersymmetry, a crucial part of string theory, predicts the existence of superpartners for known particles, which have yet to be observed. The third challenge is the lack of uniqueness within unification theories. Multiple variants and solutions within each framework complicate the identification of a single, definitive theory. This diversity has drawn criticism as it makes these theories appear adaptable and challenging to test. For instance, string theory has evolved into various versions, each with its own set of assumptions and predictions, making the pursuit of a conclusive toe more complex. The fourth challenge is the mathematical complexity associated with unification theories, especially evident in string theory, which relies heavily on advanced mathematical tools. While the depth of mathematics reflects the theory's elegance, it poses a formidable challenge for physicists and mathematicians, demanding a profound understanding of intricate mathematical concepts and abstract multidimensional spaces. Amidst these significant challenges, alternative perspectives have emerged, questioning the idea of a single, all-encompassing theory. Perspective 1 suggests that the universe might inherently be fragmented, with different phenomena described by different theories. This practical viewpoint prioritizes specialized theories and the establishment of connections between them as necessary. Perspective 2 proposes that the complexity of the universe may arise from simpler underlying principles, not necessarily confined within a single theory. It seeks to uncover the fundamental rules or interactions giving rise to diverse phenomena. Perspective 3 advocates a pluralistic approach, wherein multiple theories and frameworks coexist, with an emphasis on harmonizing and complementing these theories to achieve a more comprehensive understanding of the universe. The philosophy and implications of a theory of everything. The concept of a theory of everything goes beyond science, raising deep philosophical questions and broader societal impacts. It prompts fundamental inquiries about the very nature of reality, human understanding, and its influences on science, philosophy, and society. Let's explore the philosophical aspects and wider implications of a TOE. The pursuit of a TOE initiates philosophical inquiries, some debated for centuries. It challenges the limits of human knowledge, prompting thoughts about the essence of knowledge and whether we can fully comprehend the universe. Is a TOE the ultimate boundary of human understanding, or are there realms beyond it that we can't grasp? The debate of reductionism versus holism adds another layer. A TOE may support reducing complex phenomena into fundamental laws, raising questions about whether we can truly understand the universe by breaking it down to its smallest parts, or if we need a holistic perspective that considers emergent phenomena. Different philosophical views exist. Some see a TOE as an accurate representation of reality, while others consider it a practical tool for prediction and manipulation, possibly without an underlying objective reality. Unification, a central concept in a TOE, prompts inquiries about the universe's simplicity and elegance. Does the universe possess fundamental elegance and unity that a TOE can reveal? Or is its complexity a result of various layers and emergent properties? Beyond physics, a TOE has profound implications across science, philosophy, and society. In science, a successful TOE would redefine scientific understanding and approach to fundamental questions, possibly revealing limits to empirical science and opening new frontiers. Philosophically, it stimulates discussions about the metaphysical nature of the universe, necessitating revisions and extensions of the philosophy of science and affecting existential considerations. A single, all-encompassing TOE is not guaranteed, and alternative approaches may prevail. Furthermore, various cultures and societies might interpret and respond to a theory of everything differently, possibly resulting in a range of ethical, cultural, and even theological outcomes. This diversity in interpretations could enhance the philosophical discussion about a TOE, allowing for a wide array of perspectives on the fundamental nature of reality and human existence. If you enjoyed exploring this topic, be sure to like, subscribe, and hit that notification bell for more fascinating pop culture insights.